Welcome students. Today we are going to study ultraviolet and visible spectroscopy. So we will be discussing today basically absorption and intensity shifts. Effects of substituents on pi to pi star transition. When an atom or group enters the molecule, they change Emax and lambda max in UV spectrum. On this calculation, four types of displacement are there in the absorption peaks. The four shifting effects that will be discussed here are presented in the figure drawn on the next slide. So these are the four types of absorption and intensity shifts. The first is bathochromic shift, or we call it red shift. Second is hypsochromic shift or blue shift. Third is hyperchromic shift. And fourth one is hypochromic shift. So we have drawn here two figures. First figure is showing bathochromic and hypsochromic shift, and the second figure is showing hyperchromic shift and hypochromic shift. So let us discuss all these four types of shifts in detail by the help of examples. So the first one is bathochromic shift. We call it red shift also. The shift of absorption to a longer wavelength due to substitution or solvent effect is called bathochromic shift or red shift. Now for example, benzene absorbs it 254 nanometer while toluene absorbs it 261 nanometers. Thus the substitution of CH3 group in benzene causes bathochromic shift in the absorption band of toluene. So here we can see benzene, lambda max is 254 nanometers, and when there is substitution of methyl group in benzene, the lambda max is 261 nanometers. So there is an increase in the value of lambda max. That is the shift of absorption to a longer wavelength due to substitution. So this is bathochromic shift. Here by the help of, in this figure, we have shown the bathochromic shift. So you can see the arrow at the top is pointing towards the right, that is increase in the value of lambda max. So the lambda max is shifting towards longer wavelength. In the next example, we can see conjugation of double bonds also causes bathochromic shift. Ethylene absorbs it 163 nanometers while 1,3-butadiene absorbs it 217 nanometers. So here again, due to conjugation of double bonds in 1,3-butadiene, the lambda max is 217 nm of 1,3-butadiene. So it is again, in this example also there is the absorption maximum is shifted towards longer wavelength. Next is hypsochromic shift or blue shift. The shift of absorption to a shorter wavelength due to substitution or solvent effect is called hypsochromic shift or blue shift. It may be caused by the removal of conjugation and also by changing the polarity of the solvent. Now in case of aniline, the absorption maximum occurs at around 280 nanometers because the pair of electrons on nitrogen atom is in conjugation with the pi bond system of the benzene ring. In its acidic solutions, a blue shift is caused and absorption occurs at shorter wavelength. That is approximately around 203 nanometers. In anilinium ion formed in acidic solution, the electron pair is no longer present and hence conjugation is removed. So here in this example, Again, we can see the absorption maximum is shifted towards shorter wavelength. So this is the figure showing hypsochromic shift or effect, and here you can see the at the top of the arrow is pointing towards the left, that is the absorption maximum is shifted towards shorter wavelength, and this is called blow shift or hypsochromic shift. Now next is third type of shift, that is hyperchromic shift. When a substituent group causes increase in the intensity of band, then the effect is called hyperchromic shift. For example, the Emax for benzene is 7400 while styrene has Emax 14,000. Thus the substitution of vinyl group in benzene ring causes hyperchromic shift. Or basically it is an effect due to which the intensity of absorption maximum increases, that is Emax increases. So here in this example we can see the value of Emax for benzene is 7400 and in case of styrene the value of Emax is 14,000. So that is there is an increase in the value of Emax. So here is a figure showing hyperchromic shift. You can see the arrow is pointing in the upward direction. That is, there is an increase in the value of Emax. So this is a figure showing hyperchromic shift. Now the fourth type of shift is hypochromic shift. When a particular substituent group decreases the intensity of absorption band, then the effect is called hypochromic shift. So basically, the intensity of absorption maximum decreases. That is, Emax decreases. The introduction of group which distorts the geometry of the molecule causes hypochromic effect. For example, biphenyl absorbs at 250 nm, 250 millimicron, Emax 19,000, whereas 2-methyl biphenyl absorbs at 237 millimicron, Emax 10,250. So here again you can say the Emax for biphenyl is 19,000, whereas the Emax for 2-methyl biphenyl is 10,250. So that is, there is a decrease in the value of Emax. Now this decrease, it is due to the distortion caused by the methyl group in 2-methyl biphenyl. So here this is figure showing hypochromic effect. So there is a decrease in the value of Emax, that is the intensity of absorption maximum decreases. So you can see the arrow is pointing in the downward direction. That means there is a decrease in the value of Emax. Now we'll summarize all these four shifts by the help of these two figures. So here in the first figure we have shown red shift or bathochromic shift. So here the lambda max, there is a shift, the lambda max is shifting towards longer wavelength. Okay, now in case of hypsochromic or blue shift, so here the lambda mix is shifted towards shorter wavelength. So this is blue shift. Now in the next figure, we have shown hyperchromic shift and hypochromic shift. So in case of hyperchromic shift, there is an increase in the value of Emix. This is hyperchromic shift. The arrow pointing upward, and then next is hypochromic shift. The arrow is pointing in the downward direction, and that is there is decrease in the value of Emix. So these are all the four types of effects. So you can add some more examples. Thank you so much.